Hi, I'm Andrew Pan, and I'm here to talk today about my project called Enzyme Rate Enhancement using Janus Micromachines or micromotors. This work was done in the lab of Dr. Todd Selchek. So some background. Enzymes are widely used in both academia and industry with a lot of potential applications in the food processing industry, waste removal, brewing, and even to generate pharmaceuticals. However, to be used in industry, enzymes must be commonly immobilized onto a substrate, which enables their reusability and stability. However, one drawback is a loss of activity following immobilization. This is often due to a change in the 3D conformation of the enzyme as a result of immobilizing it. Thus, the potential of increasing the activity of an immobilized enzyme could offer great financial benefit by dramatically increasing product yield of an industrial product. One potential method of this rate enhancement lies in exploiting self-actuating microparticles or micromachines to create on-the-fly recognition. So what this is really doing is you can bind potentially your enzyme onto a substrate that can move itself around a sample. And this principle has actually already been demonstrated to enhance oligonucleotide binding to a complementary strand, antibody ligand binding, leptin carbohydrate binding, etc. Silica particles that we use in our lab can be converted to Janus particles by selectively coating one hemisphere with platinum. This asymmetric surface chemistry enables particle self-actuation upon reaction with hydrogen peroxide because the hydrogen peroxide, as seen in the image, only reacts to the platinum hemisphere, and as such, the reaction is distributed only on one half, and this drives particle motion because there's a net force moving out away from the platinum side. If the whole particle is platinum, there'd be a net force of 0, thus the particle would stay in place. We use horseradish peroxidase, or HRP, as our enzyme of choice. It is common in biochemical research for the ability to amplify a weak signal by generating a colorimetric product. For our intents and purposes, we reduce ABTS to ABTS+, which is the colorimetric product in the presence of hydrogen peroxide. This we can read on a spectrophotometer or a plate reader at the absorbance wavelength of 420. To create our Janus particles, we take 0.96 micron silica microspheres, prepare a 130 ethanol solution of particle volume in solution volume, pipette 2 microliter drops from the solution onto a glass slide that has been sonicated in deionized water. Then this is to form an optimal monolayer on the slide so that particles don't stack, and therefore when we coat the slides in the following step using metal evaporation of 5 nanometer platinum that is stuck onto the particle using a 5 nanometer titanium layer inside the clean room, therefore the metal is evenly distributed across the particles instead of having a clump together. We then remove the particles using a cell scraper and filter out the particles using a 5 micrometer syringe filter to ensure that there's no metallic debris in our sample. We then conjugate horseradish peroxidase onto the silica surface using aptase, which modifies the hydroxyl groups and converts them to an amine group, and we cross-link the amine group of the particle to the amine group of the enzyme using glutaraldehyde. Using scanning electron microscopy, we can show that the particles that we have synthesized in this method have a clear even split of platinum on the particle surface, in that one hemisphere is covered and coated in platinum while the other is uncoated in silica. We then do a test where we have our HRP, as described earlier, we bind HRP to the silica hemisphere, and we compare the Janus particle HRP complex to just a blank silica particle that we don't cover with platinum. And we can see at all kinds of concentrations of hydrogen peroxide at a singular concentration of ABTS, our Janus particles demonstrate much higher turnover rates. This is because we also want to see, because hydrogen peroxide both increases the particle velocity and it can also increase slightly the reaction rate itself just by the nature of reacting with ABTS. We want to see, is there a sharper increase when we increase hydrogen peroxide, which we do see, and this little spike that we see in both the curves is actually found in a previous study where there's actually a sweet spot of hydrogen peroxide, because too high of a concentration of hydrogen peroxide does lead to decreased turnover rate, because in excess it converts to a different product that dilutes your colorimetric signal. We also want to make sure that the particles themselves have no effect on the enzyme turnover rate or on the colorimetric signal that we generate. And we see clearly that in both in our platinum silica Janus particle and our blank silica particle, when we compare it to the enzyme and non-enzyme bound states, we only see appreciable turnover rates or a change in the absorbance at 420 in the enzyme bound systems, meaning that the particles themselves do not affect the signal. Now we compare just at 1.75 millimolar of ABTS and 4 millimolar of hydrogen peroxide, the platinum silica Janus particles versus this pure silica HRP complex. While they both demonstrate appreciable turnover rates, it is clear that the Janus particles demonstrate a much higher turnover rate and sustain this rate for a long time span at 10 minutes. So it's not just one sudden spike up and then a drop, it is a continuous turnover of substrate to product. However, it does plateau, and this may be because the faster substrate conversion leads to reactant depletion, thus decreasing the rate after a certain time period. We then wish to, again, see this behavior at various concentrations of ABTS. And we can generate while it's not perfect, a Michaelis-Menten curve for both Janus and non-Janus enzyme-bound particle systems. And we see a very high rate enhancement in our Janus particles compared to non-Janus, to the extent that when displayed on the same graph, the curve of the non-Janus enzyme complex actually almost appears to be a flat line. This is up to an order of magnitude enhancement at several concentrations using the Janus enzyme particle complex. One very interesting finding from our work is that because we hypothesize it's a particle motion that is driving this increased turnover rate, surely if we can slow down the particles, then we can demonstrate, then we can prove that, or we can get closer to proving that this idea is true. And one way of slowing down the particles without affecting the hydrogen peroxide concentration is actually increasing solution viscosity, which we did by adding glycerol. And in this case, for both Janus and non-Janus enzyme-bound particles, we only see a very appreciable, significant loss of activity in the Janus particle complexes at 5% and 2.5% glycerol, indicating that it is the motion that is driving this increased turnover rate, because a loss of this motion leads to a loss in enzyme activity. We demonstrated that horseradish peroxidase has a higher turnover rate of ABTS substrate using the Janus particle motion to drive this on-the-fly reaction, which we hypothesize increases the probability of enzyme-substrate collision. This dramatic increase in reaction rate may prove industrially useful to improve yield of an important product. Another interesting application in particular is maybe using this to drive formation of product in very low substrate concentrations, which can eventually save costs. Future goals can characterize this Michaelis-Menten kinetics at different concentrations of hydrogen peroxide rather than just 4 millimolar, and we can calculate the kcat if we can actually use a Bradford assay in the future to quantify how much enzyme is bound on each surface. Glycerol tests at concentrations of 1 to 5% and 1% intervals, and seeing the effect and doing a Michaelis-Menten curve to see the loss or change in kcat. Do the reaction at different temperatures, which can affect the solution viscosity, and see if a lower viscosity solution can increase Janus particle turnover rate, and maybe use an industrial relevant enzyme to generate an industrial relevant product using this method. Citations. Thank you very much.